Hi students, welcome to Inside Physics. In this session, we are going to see what a semiconductor diode and what is a forward biasing. So, semiconductor diode, di means two. There are two materials, p-type and n-type, as we know in extrinsic semiconductors, p-n junction diode. So, we will form a junction with p material and n material. The formation of p-n junction is already told in another video of my previous videos. So, now we consider what is biasing. Biasing means we apply an external voltage to this p-n junction diode. So, di means two, there are p material and n material. There will be a thin wafer layer like very small thickness, almost in nanometers. So, this is like, it looks like a big material, but it is like very thin nano wafer like material. So, it is n-type. When we combine these two materials, there is a junction between p-type and n-type, that is called junction of the two materials. So, there is a slight gap between the attached p and n-type materials. So, what is biasing? Biasing means we actually apply an external voltage to the p-n junction diode. So, these are the metallic plates. I have written here metallic plate. So, these metallic plates are useful to attach the battery. Here we attach a battery to the metallic plates to supply the external voltage. Why we supply external voltage means we actually need to study the current flowing through this junction diode. We need to study how much current and how the current will flow when we are biasing, means we are applying the external voltage. So, what is forward biasing? So, biasing, there are two types, forward and backward. So, forward biasing means we apply the positive terminal of the battery to p-type material and negative terminal of the battery to n-type material. So, here I will write p and n. So, this is the positive terminal of the battery and this is the negative terminal of the battery. So, this is the symbol of p-n junction diode. This symbol indicates, the arrow indicates the conventional current. Conventional current means the current direction which is opposite to electron flow. So, here are the indications of p-type and n-type material, and here I have written depletion region. What is depletion region? So, actually in p-type and n-type materials, the electrons are the majority carriers here in n-type and holes are the majority carriers in p-type. So, because of the mutual potential difference developed between these two, here the electrons per unit volume, concentration of electrons per unit volume is more, and here the number of holes per unit volume is more. So, here electrons are minority, here majority. Here holes are minority, here the holes are majority. Charge carriers. So, they actually shift their places, they carry the charge. So, in this equilibrium, whenever the equilibrium position, the electrons will actually cross this junction. Okay. So, a junction is a line between p and n-type materials, and the depletion region is the space around the junction, the space, the small space left side, small space right side. So, here why I have written this negative charge symbol on the left side, positive charge symbol on the right side means whenever the diffusion happens, diffusion means due to the potential difference, the electrons will cross the barrier, that means the junction, and they will actually come into the p-type material. At the same time, because of the concentration gradient concentration gradient means the concentration of the holes per unit volume here is more. So here it is less. So there is a gradient which is moving high to low. Okay, so that means the holes will move towards the N type and the electrons will move towards the P type. This is actually, they are moving on the basis of gradient, so it is called diffusion. So based on the diffusion, the electrons will accumulate in this side, holes on that side. So majority negative charge will accumulate just besides the junction, and the holes, the positive charge will accumulate just beside, more on the just beside space of the junction. Why? Because see, the attraction between the positive charge, that means hole side and electron side, is more because of the narrow space. So the accumulation of negative charge is more here and the positive charge is more here. So overall the charge accumulation, negative this side, the electrons will be flowing this side and holes to that side. The charge accumulation just besides the junction is more. So the concentration of the electrons coming from the junction away from this side towards this side will decrease. At the same time, the whole concentration moving away from the junction will decrease. That is called gradient. So the gradient is coming down towards this side more here and gradually decreases. The whole concentration is more here and gradually decreases when going away from the junction. When this happens, the diffusion will come to an end when there is an equilibrium position. That means, see, the whole concentration here will increase and the electron concentration here will increase. The more hole concentration here will prevent the further reach of the holes to that side, and the more negative charge concentration here will prevent the further electrons to move to this side. So there is a potential which will stop the further movement of holes and electrons, that is called barrier potential. So depletion region, barrier potential, these two are the important definitions in this concept. And now we come to the point, when we apply external voltage, what happens? When we apply external voltage, the built-in potential, already there is a diffusion happened and there is a potential which is also called barrier potential or built-in potential, that is represented by V naught, and the applied potential is V. This is barrier potential and or built-in potential. This is applied potential. So here V naught minus V will be giving the potential developed across the PN junction after the external voltage is applied. If the external voltage applied is less, that means the barrier potential, equilibrium barrier potential, can be reduced by applying the external voltage. Why? Because the net voltage, the potential difference, the applied voltage makes further the electrons will be moving towards the P region. After reaching the equilibrium position, so the equilibrium barrier potential is reached. Then we apply the potential. Here the current direction is shown like here. When we apply the potential difference, the resultant potential, the net potential will be built-in potential minus the applied voltage, because they are in quite opposite direction. So what happens after applying the potential means, see, the potential, the EMF force, here the electron flow is denoted like this, and the conventional current is denoted in this direction with this arrow. So After reaching the equilibrium position, the EMF of the battery will further push the electrons towards this side, and the positive terminal of the battery actually pushes the holes further to the N region. So the further push because of the electromotive force will actually increase the negative charge further in this side and increase the hole concentration, that is positive charge, further on N side. So what actually we are making by applying the external voltage means we are actually decreasing the depletion region. The depletion region, that means the space around the junction both sides will decrease. Depletion region doesn't have any charges, it is without charges. A region with no charge is called depletion region. And the barrier potential, the potential at which further movement of holes and electrons will be stopped at equilibrium position, will also be reduced. If the applied voltage is very small and the depletion region will slightly, here I have denoted with two arrows, this is compressed, and the barrier potential is also reduced very small quantity. So if the applied voltage is more, so the barrier potential will also come down with this relation, and the depletion region also further decreases. So all in all, what happening is the current flowing through the junction diode is a combination of movement, hole movement towards the N region and electron movement towards the P region because of the concentration difference, that is because of the gradient of the concentration of holes and electrons. This gradient makes the movement possible. So the combination of current due to hole concentration, that is conventional current, hole concentration means that actually we consider the conventional current, plus conventional current is because of holes, and the current flowing through because of the electron diffusion, electron flow. Okay, current due to electron flow and conventional current due to movement of holes. Here holes movement. So sum of these two currents will actually be in a milliamperes. Okay, very small current flowing through the junction diode. So how the current is actually calculated means, see, the gradient, the negative concentration is more here and becomes low when you are coming in this way. The whole concentration is more at the junction and it becomes very low going away from the junction. So what happens, because of the concentration difference, the gradient, the negative charge will actually flow away from the junction and the positive charge actually flow away from the junction. So positive charge is our conventional current, this is the whole current in this direction, plus the negative charge in this direction. Negative charge direction is considered opposite to the conventional current. So electron flow in this direction, that means here also the current is considered in this direction. This is electron flow, this is conventional current. This is positive charge, that means whole current is always in this side and the electron flow in this side. So conventional current is thus that side. So this current plus this current. So all in all, the current is in one direction. The current flowing through the PN junction diode is a combination of conventional current, that hole movement, and electron flow. Actually the current flow direction is opposite to the electron flow. So both are summed up. That is actually calculated with in milliamperes, mostly very small current. This is called current flow because of the forward bias in a PN junction diode. So we'll calculate the current with some sensitive instrument like galvanometer. So this is how the forward biasing is done, and we observe what is the current flow and how much the current will actually flow in a PN junction diode while forward biasing. This is the concept. In the next topic we will see reverse biasing.